and using it, but possibly without fully understanding it. So I just want to break it down to a little bit what's happening under the hood. So I guess this is the first of our asynchronous under the hood sessions. And to do that, we've got this little snippet here. If someone could just talk me through that snippet, it would be fantastic. Just explain what it's doing and what's going on. So what happens? Anyone? So read it top from bottom and then tell me what bit runs first and all those sorts of things. It should be. Says it's streaming? Yeah. Yeah? Good. Anyone then?
Is it 3 parts? So we got the top name and then the second one is prime and the third is state.
Say it a little bit louder, Raj.
Is A will be the function.
Yep, so we've got 3 functions, right, for a start. Function A, function B, and function C. Do we invoke any of those?
Yeah, you're invoking function A.
We invoke function A. What does function A do? Invoke function B. What does function B do? Invoke function C. What does function C do? Ooh. Console.trace. What does console.trace do? It shows a stack trace. Now what is the stack? The JavaScript stack. So let's not worry about the order just this second. What did you say it was show anyway? You said it shows C, then B, then A.
Yeah.
So console.trace will show function C, function B, and then function A.
Yeah.
That's your guess. Okay, nice. So the stack trace is the current list of tasks that JavaScript is running or needs to complete. Yeah, so the stack is literally well, I'll show you a diagram, right? How to explain it. Just show you a diagram instead. It's one of those, right? So function A, when we call function A, gets added to the call stack. Then that calls function B, which gets added to the call stack, which calls function C, which gets added to the call stack. Once function C gets completed, it gets popped off. Yeah, function B complete, function A complete. Alright, so this is in general how all of your tasks that you queue up in JavaScript run. And the tasks on the call stack are blocking. By blocking, we mean that function A cannot complete now until function C has completed. Yeah? So it's a first in, last out sort of approach. The call stack is, yeah? A gets in first, but because these other functions get called before it gets completed, A just sits there hanging while all these other tasks complete. So this is what's going on under the hood in the engine in your browsers, in the JavaScript engine in your browsers. Does anyone know the name of some common JavaScript engines? Question, Kieran. Yeah, yeah. This is not recursion. No, the function's not calling itself. It's calling a different function. Yeah, these are discrete functions. This is just queuing tasks, right, in the browser essentially, or in the JavaScript engine.
So what was the question?
So the question was, do you know any names of common JavaScript engines? What runs in Google Chrome, for example? What runs in the V8 engine? Yes. Where else has the V8 engine been adapted to run? In Node. Fantastic. Yeah. So that's the benchmark at the moment, really, is the V8 engine, right? That's our best engine for running JavaScript code. Some other browsers would probably not like me saying that. Other browsers such as Firefox. What does Firefox use? Anyone know? Spider Monkey. All right.
What?
Yeah, it uses the Spider Monkey engine. And how about Microsoft Edge?
They're going to switch to V8.
Are they going to switch to V8 as well? So there you go, right? They've developed their own one and they gave up because it's not as good as the other competitors. So similar, I guess, to using the Linux kernel now, as it's Linux kernel or Linux shell. I can't remember what they're using. They're using something of Linux, right, in Windows now. But Chakra is what it's called. Yeah.
Oh, it's Linux kernel, sir.
Huh?
It's Linux kernel.
Linux kernel for the Microsoft. Okay, nice. Yeah. But that's the idea. So this is all synchronous code. This is an example of synchronous code. By the way, Keyvon was right? He said, what happens when we get the stack trace when we're inside of function C? So inside of function C, that point there, what will the stack trace be? Let's have a look at the code. Are you off with that?
Yeah, sorry.
That's all right. Yeah. Oh, he's not off.
No.
Oh, okay.
So,
I was being serious. I wasn't actually joking and turning you off for standing up. I was wondering if you had to leave. So console.trace is quite a new addition, I think, to the console object. And we can see clearly there what is at the top of the stack. Function C is at the top of the stack. So that means if we had some extra code in here of function C, all of that code will get run first. Then function C will pop off the stack and function B will resume. So I really encourage you to play around with console.trace. In DevTools, you might have some snippets by now, maybe some of the answers or attempted solutions on the Kadiri platform. Put a console.trace in there at some point and see where it stops and see if you can work out what still needs to run and in what order these things have been added to the call stack. Yeah, really useful for understanding how your JavaScript programs are working. The anonymous bit is just essentially saying where did the console.trace come from, I think that's what it's doing. I've never quite worked out exactly where it references that. But I think that's a reference to the console.trace itself, which I guess is at the end of that function. Yeah. So, oh no, it was there, wasn't it? So what invokes? Yeah, to begin with. Right. Yeah. So that's all examples of synchronous code. One thing, then the other, another, blah blah blah. What happens when we introduce some asynchronous method or code to our representation of our JavaScript engine or our environment in which JavaScript runs? Where are we? Yep. So we had that one. What are some examples of some asynchronous methods or code?
we use the
Then, so using promises, exactly, yeah. A promise would create a bit of asynchronous code that would not go directly onto the call stack. It would go somewhere else, which I'm going to show on the next image. Let's think of a few other examples first. What else would create something that is asynchronous? We've come across at least two other examples.
I don't know what it is when you're pulling information from the back end.
When you're pulling information from the back end, so a fetch request from fetch API. What does the fetch API belong to? Is it part of JavaScript or part of something else? Something else? What is the something else?
Yeah.
No, it's not. It's not a React method. No.
it wasn't it HTML?
HTML, well, it's a browser method, right? It's a browser API. So lots of APIs built into the browser. A lot of those will create events, and then it's through the events that we will communicate with the JavaScript engine itself. So anything that triggers an event, like your on-clicks, all those sorts of things, they don't go immediately onto the call stack. They go onto another task queue. Yeah? As well as that, we've got callbacks themselves, the setState method, all of these, even all the some of the hooks, right? They're going to be asynchronous. So some examples are on the left-hand side of the web APIs. So a network request handler, which is pretty much what Jack said, I guess, like the fetch API. Some sort of timer event, such as set timeout, set interval. Yeah, other DOM events, mouse click. That's going to queue some tasks on the event queue, and only when the call stack is empty, so only when there's no other code to run or nothing to complete, I guess, in your main JavaScript program, then these event queue tasks will run.
Then how do the timer event handlers execute at the right time? Like imagine there were many other tasks. Like they would jump the queue or...
But don't forget the call stack is only going to have invoked one function at a time. So what does an event listener usually do, right? It listens for an event, and then when that event gets triggered, a task gets put on the event queue, and a function gets invoked, right? Your event handler gets invoked. Yeah, so the event handler, that code will run essentially to handle the task. And as long as you haven't called any other functions in the meantime, then the event handler and the tasks are the only things that exist on your call stack, so they get handled at the right time. If your event handler also called 10 other functions in your JavaScript code, then it's a bit of a problem, right? Because all of those other functions would have to be completed before you could handle your event. But usually that's not the case, right? The event gets triggered, and we've just got one function to handle that. Cool. Yeah, so let's have a look at the timer event handler example. We have here, yep. All right. So we have a slow task, we have a fast task, and then we invoke a combination of fast and slow tasks in our application. What order are they going to complete in?
Sorry, why is that one task is fast and the other one is slow?
Okay, so that's a really good point to begin with. Why is one fast and why is one slow? So what does the fast task do?
Just
Console log.
Not much, just console log, yeah? So it hasn't got a lot of work to do. That should run almost immediately. What does the async slow task do? The asynchronous slow task do?
Sets a 2-second timer of delay.
Oh, don't worry about that, it's me playing around, sorry. Yeah, the async slow task sets a timeout to run another bit of code in how long?
2 seconds.
In 2 seconds, it says it there. So does the slow task run straight away?
Ah, okay. So
So it's fast task, then async, and then slow task.
it's not that slow
No.
task is slow. You are invoking first another function that asks it to take some time before.
Yeah, if you like, then the async slow task, I guess I could call it async slow trigger or something like that. So it doesn't actually run a task, but it triggers a different task. If I do that, of course, I need to make sure I change it everywhere else. Yeah. So if we want to be really picky, we can of course number these, right? I guess we can call it fast 1, slow 2. Oops, that's fast, right? So keep thinking about what order these are going to come back in. Are they going to come back in the order that they've been invoked or not? I suppose we should have the numbers like that, right? 1, 2, 3, 4, 5, and 46. Yeah. How am I going to get this message passed to my tasks?
So was that right?
So this fast 1 that I put in here,
Yeah.
how am I going to use that value inside of my fast task? Back to functions 101. Huh? So I want to use this value. At the moment, am I using the value? No. How can I log what task I'm on?
How do you want to use it?
I want to log it, right? Let's say fast task, fast 1 finished or something like that.
You have to add an inside the function.
Yeah.
Yeah,
Let's have an argument. So that could be my task identifier, and then I could use backticks instead. Yeah. Just to check you're awake, right? Ask you some off-topic questions to throw you off. Wow, people need their sleep today. Okay, so fast 1 task finished, that would say, right? Or slow 2 or whatever. So I could do the same thing for, where does this go? In there?
Yeah.
No. It can go in there as well, I suppose, but I think you'll find that the slow task won't reference the correct value, and that at the moment will be undefined task there. What function is this triggering?
Ah, yeah.
Yeah, so it needs to first go in there, and then of course, ooh, set timeout. Does it allow you to pass things like that into set timeout? Don't know. Let's try it. Okay. So now hopefully we'll get a bit of feedback about which one completed first. Maybe it's number 6. I don't know. Which ones do you think complete first?
First 1.
Task 1.
Yeah.
Then what? Slow 2, fast 3, something else.
Those are 2 seconds.
I think fast 1, fast 3, fast 5, fast 6, and then slow 2, slow 4.
Yeah, I
F.
agree with you.
2. There's no F2. F3, F5, F6, S2, and S4. Something like that. Okay. But didn't we just say that previously, or if I can find my, previously, when we call a function, doesn't that function have to run to completion until everything in that function is run, and then it can get popped off the stack?
I don't know how to translate that to the other situation.
So the difference is set timeout is asynchronous. So when that triggers something, to avoid the whole programmer having to wait 2 seconds, what it does is it queues the slow task on, I really need to work out my windows, right? It queues the slow task over here, right? Timer event handler sticks the task over here, which means we can call fast task 3, and that goes on the call stack, yeah, and so forth. So that's why your answer is correct. Bom, bom, bom. Yeah. If this was normal blocking code, then the slow task would just completely stop all these tasks below it running. Alright, because there's no way we can trigger something else until we've run all that code inside. Which is why things like your fetch, your set timeout, even your set states are asynchronous, so that we can continue running code further down the program without interrupting the user's experience. So hopefully that gives you an idea of why asynchronous code is so important, right? If the user just had to sit there waiting for ages and they couldn't do anything on your application at all, then they'd probably just shut the window and leave. So yeah, let's just prove that we're right.
Is there ever a time where, if, let's say you had like 20 fast tasks or whatever, and obviously there is an actual time that it takes for those functions to
That was unexpected.
be
I've,
called?
huh?
So if you had like, I don't know, 20 fast tasks, obviously there is a time that it takes to actually return each of those functions. Would you ever get to a point where there's so many fast tasks that you're trying to do,
Yeah.
that set time actually completes before you get to that fast task?
No.
It's
Why?
It's instantaneous.
Why?
It's instant.
No. Even if you had, I don't know, so many fast tasks that it took them 5 seconds to complete, what's going to complete first?
All the fast tasks still, because the way that it works in the asynchronous code, the asynchronous code would happen after the non-timer tasks.
Actually, that's a good point. So
That's what I'm trying to work out.
it depends on how your program is set up, because if all the fast tasks were put on one by one, yeah, so you kept just getting one on here and then it get popped off, yeah?
Yeah.
And you had this event over here waiting 2 seconds until there was free space on the call stack, then the task would run after 2 seconds, because the call stack would get emptied at some point between fast tasks, and then this timed task would run after 2 seconds. So yeah, it could run in between your infinite number of fast tasks, definitely. If you had a fast task that called an infinite number of fast tasks, yeah, so effectively you've got one function here that calls many other fast tasks,
Yeah.
that's going to take up all the call stack, right, for let's say 10 seconds. And therefore the call stack won't be cleared until after 10 seconds time, and then your slow task can run after 10 seconds. Did that make sense at all? Have you just opened up a can of worms?
Some directions are better than others.
The set timeout, instead of taking 2 seconds, would take
As long as it takes the full stack.
As long as it takes that other slow or slower function to run. Yeah.
So the 2 seconds is like a minimum.
The 2 seconds is like a minimum. Absolutely. Yes. Yes. Yeah. So that the task can only run after 2 seconds if the call stack is empty. If the call stack's not empty, if there's some other blocking code going on, then it has to wait longer.
And in the call stack, there could be only one function at a time.
No, in the call stack there could be infinite. Well, however, you've probably seen it call stack exceeded at some point. You've got an error if you run some sort of infinite loop.
Yeah.
Yeah, and that's because you're calling things again and again, and the call stack blows up, right? There's too many tasks to run. It can't hold them all in memory. Every time something's on the call stack, it's in memory, waiting to be processed. So it holds a lot of tasks, the call stack, but there is a limit. forgot totally what we were talking about, but I think we're pretty much done anyway. I don't want to go too much further today. So yeah, I don't think this worked because of me trying to pass that argument in there. So in other words, we're just going to have to say nothing in there. Alright, so coming back to that. See all the fast tasks done, 1, 3, 5, 6. And debugger, why have I got a debugger? Don't know. Oh. I had 4 slow tasks go. Why? Interesting. I think this could be DevTools just being weird. Let's try once more. It's just putting random breakpoints in for me. That's better. Once more. Fast, fast, fast. 1, 2, boom. Yeah? And then the slow tasks finish pretty much at the same time. So why did they finish at the same time? It didn't take 4 seconds.
So why don't they? Why do they?
Yeah, well, how did they both finish after approximately 2 seconds rather than taking one take 2 seconds and one take 4 seconds?
But how can we know that didn't happen?
Well, you count, right? Essentially, I can put a timer on if you want, but
no,
are you ready? Watch the console. I'm going to hit.
Esteban will answer.
Ready? Yeah, I'm sure he will, but 1 second. So we got fast, boom, together, yeah? After 2 seconds. Esteban, yes?
Because even if they get triggered after the other ones,
Yep.
they get like the first slow task goes to the queue and
Yep.
right after goes the other one.
Yep.
So that's almost, I don't know, a microsecond or something like that.
Yeah.
So that's why they look like they are at the same time.
It's the same as the fast task, right? The fast task happens like immediately after the set time. It's the exact same in both of them.
Yeah, exactly. So, because the slow task is asynchronous, it doesn't block any of the other tasks from either running or getting queued. So the second slow task essentially gets queued a few microseconds after the other slow task, and then the first slow task will go onto the call stack, get run. That takes no time at all, and then the other slow task is free to do the same. Yeah, so it doesn't have to wait 2 seconds for the actual inner code bit to run. They get queued almost straight after one another. They both have to wait 2 seconds from when they got queued, and then they're free to run. Yeah, it's definitely a workshop. And I can just send you those couple of snippets. But yeah, I really want you just to get this idea in your head. There's a fantastic talk. If you want anything to do with the event loop, just look up Jake Archibald. And I believe he works on the V8 engine, but I'm not sure. Does it say what he works on here? If he doesn't, he has a great understanding of it. It just says Googler once swam to the end of an infinity pool. That's quite impressive. Oh no, they're just the ones that go over the side, right? I hope he survived. But this, essentially, in the loop. Oh, good music as well. Maybe. Ed's loving that at home. He's rocking out at home to that. But anyway,
as you begin to sneeze,
this is the talk.
Shuts down.
And
like the first thing you lose is the ability to talk. Then you pull a stupid face.
It's well worth a watch. He's linking it to sneezes, I guess, blocking code to sneezes. You're unable to do any other functions when you sneeze, right? But he's got some wonderful diagrams, some nice animations here going on.
fine, I'll get round to it.
Yes,
So
this
it
is
runs the first
these are our
callback,
this is our task queue that we
goes around
had.
the event loop, and runs the second callback. And that's tasks. And it'd be pretty simple if that's all it was, but it gets more complicated when we think about the render steps. And this is what the browser uses to update what's actually on the screen.
So he's trying to model it all together, right? The call stack, the event queue, the browser's own functions, the paint, the draw.
Layout, creating a render tree.
So this event loop is just constantly running, looking for new tasks.
And where it's positioned. And then creating actual pixel data, doing actual painting.
I found the visual learners in the group, right? But anyway, it's a fantastic talk, so I'll share the link, and it's well worth a watch to understand how JavaScript works under the hood, and specifically the event loop, and how it all fits in with the browser and other tasks that we queue, such as callbacks and promises.
At coding badly. But I can take very simple bits of JavaScript and create infinite loops out of them in places I least expect. But let's take a closer look at what happens when I do that. Here's a page with a GIF and some text. A big button that runs an infinite JavaScript loop. So, if I click that button, everything stops. The GIF has stopped. I can no longer...
blocking code, right?
Has kind of come to a standstill.
So your call stack is getting overloaded. Infinite loop.
So, how do you actually visualize this? Well, the user clicks the button, so the browser says, hey, event loop, I've got a task for you. Event loop's like, yeah, no problem, I'm on it. But this task never ends. It's running JavaScript forever. A couple of milliseconds later, the browser says, hey, event loop, we need to update that GIF that was on the page. So if you could just render at your next earliest convenience, that would be fantastic. The event loop's like, yeah, okay, I'll get round to that right after I finish this infinite loop that I'm busy doing right now. Then the user tries to highlight text, and that involves like hit testing, it involves looking at the DOM to see what the text actually is. So the browser says, hey, I've got a couple more items for your to-do list there. The event looks like, are you having a laugh? Like, do you know how long it takes to perform an infinite loop? It's a long time, there is a clue in the name. So that is why a while loop blocks rendering and other page interaction. But this is a good thing in practice. We look again at the code that I started with. I used to worry that this would result in a flash of content, but it can't, right? Because this script runs as part of a task, and that must